Thanks for the invitation, and I'm glad to give another talk in Lagon. I think I gave a talk a couple of years ago, so I'm very glad to come back. And yeah, I will talk about this class braid groups, which I have been working on for almost 10 years. And so these 4 papers in blue are the published ones. And recently I have some joint work with Hanzhe, Heping, and Xiaoting, which is very related. And we are also writing 2 more papers, hopefully within a couple of months. Anyway, so maybe let's start with the motivations. Maybe I need to move this down. Yeah. So my motivation to introduce this type of generalization of braid groups is to study the space of stability condition on triangulated categories, and also to have this action on the space of stability condition. You actually first need to act on the categories. So we're also interested in homological mirror symmetry. And by now, there are many works showing that the space of stability condition can be identified with model space of quadratic differentials. So we have some application of cluster braid groups to the differential side, which I think is very interesting. But for this talk, I will mainly focus on the cluster theory and Artin's braid group. So cluster braid group, that's the 2 key ingredients. And towards the end, I will maybe talk about a little bit about application to quadratic differentials. So that's the plan. First, let's recall the braid group. So a braid in a configuration is of a surface S. So this is a topological surface, and a braid in that is a configuration in the configuration space, and take the pi1 of that. So you need to have a set of points in this surface. So for example, usually you take the disk or take C, and you take, say, a couple of points, and you take pi1 in this configuration space, and you can draw it like this braid picture. And yeah, so the classical braid group is when the surface is the disk, and we will take n+1 points, which we call decorations, and this will correspond to type an. So that's why this is n+1. And the generator for this braid are very easy to see. Is that you just need to twist the neighbor ones and to have a generator bi. So for n+1 string braid group, you will have an n generator. And it's also easy to check the relation in the braid group. One relation is commutative relation is when you have the 2 this twist, which is far away, then they commutate. By the way, the product is just putting them together like in the fundamental group. And the other relation is also well known as the braid relation, is that bi +1, bi equals bi +1, bi +1. Yeah, so like ABA equals BAB. And a little bit difficult, I mean, not that difficult, but to show this relation, all the relation needs some work. So I think Artin proves that this really gives you a presentation. So the generator and relation are easy to see, but you need to show that's everything. And the proof is actually you can use the standard trick in knot theory that to use piecewise linear strings to mimic the continuous braid, and then you can do stuff to show this. That's not that hard. But the generalization for this is when you have in general, you can have any diagram, but maybe let's restrict to Coxeter Dynkin diagram. and you can just algebraically associate a braid group to this type of diagrams. And the way to do that is for each vertex, you have a generator. And for any two vertices, you have a braid relation to some degree. What does that mean is that you have this type of, I don't know, degree m braid relation, meaning that you have ABA, there are m factors equals BAB continuous. And one, there's no edge connect to what has, then we have this BR2 relation, which is just AB equals BA, that's commutative. And the classical case is this weight is 3. So when you have an AD Dynkin diagram, all the weights are 3. And in that case, you will have ABA equals BAB, the classical relation. But you can also have higher version. And if you have multi-arrows, like if you have connect quiver, then this number should be infinity, meaning that there's no relation between the corresponding generator. So if you go back to previously we have this classical BRn plus 1, then it's just type AN braid group. And of course, you may more familiar with the Y group, which is the quotient group of braid group by the square to 1 relation. And for example, in type A, the Y group is just the permutation group. And this group is much easier because, for example, when I mentioned this Cox-Dynkin diagram classification is the corresponding Y group is finite group. However, even in the A2 case, the braid group is not finite. So braid group is, I think, much harder than the Y group, but they share many similar properties. Anyway, so the topological realization of braid group is known as the surface braid group. So it is just taking the pi 1 of the configuration space, but now you can take any topological space. So you can have genus, you can have boundary components. And another way to define this, for example, when S has known empty boundary, then this surface braid group can be also defined as the mapping class group of S data. So this is the surface with decorations. So you can move the decoration around, quotient by the mapping class group. Yeah. So for example, when you have a disk, if you ask the symmetry, the symmetry of the disk, meaning you have a, say, a homomorphism map from it to itself, preserving the boundary, then it's always isotopy to identity. So this group is trivial. So the classical case, the whole mapping class group of the disk with n plus 1 point equals the surface braid group, and also is the classical braid group. And also the Artin gives the presentation showing that this is the braid group of type AN. So that's the classical situation. So another thing I want to recall is that, say, if you have AD Dynkin diagram, you have the corresponding Cartan subalgebra, and you take the regular part. So it is well known that the reflection group along these hyperplanes in this Cartan subalgebra H will act and generates this Y group. And in fact, if you take the regular part quotient the Y group, then the pi 1 is the braid group. And this is related to a conjecture known as the K pi 1 conjecture, which just saying that for this space, if you take the universal cover, is contractible, meaning that the homotopy type of this space is determined by its pi 1. So that's also the relation between a braid group and Y group, and how you can produce braid group from this aspect. Yeah, so that's classically you have many realization of braid group, and we want to use the class theory to give a generalization and possibly with application to here and there. So let's recall some class theory. So class algebra is introduced by Fomin and Zanovinsky, and I assume that most audience will see this example. So you start with a A2 quiver, you put a variable in each vertex, and you can start to mutate. In the A2 case, basically this is the mutation formula. So you change one of them and to use this formula. And there's a periodicity appear, and this is the class exchange graph you get. But more precisely, in general, you can start with a quiver's potential, and this quiver usually, you can start with to a cyclic quiver, and the potential is just the sum of cycles and forming DWZ. They also give the extend the FZ's mutation formula to the case with potential, but I don't want to talk about the details. When you start, you give each vertex a variable, and you can mutate. The mutation formula, I will just go very quickly here. So you have some combinatorial rule about how you mutate at a vertex. So you need to reverse the arrows at that vertex, add something, delete the 2 cycle, and the variable changes using a kind of generalized Ptolemy relation. But the key point for us is the only thing I care in this talk is the class exchange graph. So you start with a cluster, and you mutate, and you can obtain many other clusters, and you can identify them. So if the quiver and also the variables can match, so you identify them. And then first thing is mutation is an evolution, and we only kind of need this combinatorial gadget from class theory is the class exchange graph whose vertices are classes and edges are mutation. Because later we have other interpretation of this, so I skip many detail of how you really mutate the cluster algebras, but just give you some ideas what's going on. In the type A case, the cluster exchange graph is just the associahedron. So for A2 case, this associahedron, you can obtain this by, if you look at, you want to calculate the multiplication of 4 things, A, B, C, D, in some order, and use associativity, you can have different ways to do that. So basically add some brackets, and there are 5 ways. And each time you use associativity someplace, you connect the 2-way, then you can have this picture. This is A1 times A1, and maybe this can ring some bells. So the type A3 cluster exchange graph is the associahedron. So I'm drawing this view, and later there will be another view, but this is the famous associahedron. So this is basically all the input I need from cluster theory. So if you are more familiar with cluster category, you can also just take a cluster category from quiver's potential, and then say the vertices correspond to cluster tilting objects, and the edges correspond to mutation. And then you can get the same graph. And that's kind of the only thing I need to take from cluster theory. So now what we want to do, the first thing is that the mutation, you should think this has direction. So when you mutate the cluster algebras, like you have a quiver, you have variables, when you mutate it twice, you come back. However, this is really square to 1, not that you should just draw one edge. So basically, what I'm saying is that once you have the class exchange graph, you should replace each unoriented edge with a 2-cycle. If you think this in a class tilting in class category, that the mutation is actually you have this forward mutation and also backward. It's just happened that the classical case, when the class category is 2-color BL, the forward mutation square to 1. However, if you consider, say, M class category, then you also have this forward mutation, but then it's to the M time to the power of M equals to 1. So then, in other words, that each almost the complete class tilting object has M completion, which corresponds to a M cycle in the corresponding class exchange graph. So basically, that's the correct thing to consider. But here, so what we do is that once you have this, say, pentagon, you just need to replace each unoriented edge with a 2-cycle. And the next thing to do is that, so now it's the class exchange graph after we do the oriented version. It's a one-dimensional CW complex. Now we want to add some faces to it so that we can calculate some pi1 to define the cluster braid group. So how can we do that? So for each cluster in the class exchange graph, you take 2 vertices of the corresponding quiver. And because we kill all 2 cycles, and you can assume that there's no arrow from I to J. And locally, you can mutate I or J and I. So locally, you have this piece of subgraph. And it's very easy to see that if there's no arrow from J to I, then basically mutation I and mutation J commutative. And then you can complete this local graph to double the square. So that's basically A1 times A1 case. And if there's a unique edge from J to I, and basically you are in the kind of A2 case, so you can complete this local graph to a doubled pentagon. So that's the 2 cases I show here. So at each clusters, you choose 2 vertices of the corresponding quiver, and you look at the local mutation pictures, and you can get double the square, double the pentagon. And if you have more arrows from J to I, then this sequence will continue to infinite. Like you get the classic exchange graph of type affine type A2 or A11. Then you cannot complete. But anyway, so in this local picture, there are some technical this relation we want to add, but I want to omit this technical relation. So there are some hexagon we want to glue. However, for example, in the Dynkin case, this hexagon will decompose into the things I will mention in the next page. So we won't talk too much about that. But this is the key in the surface case. What we really want to add at the moment, especially in the A11 or A2 case, is we want to add a square relation and pentagon relation in the local picture. So basically, if you start here, you start with something after you complete to double the square. We want to glue 4 squares. So at each vertex, you go 2x and you go 2y. You end up at somewhere. Then you glue a square. But you can start with at each vertex. So there are 4 squares you want to glue. So this x and y should all have subscripts. However, I omit them. And also this is a simplified version. Same in the pentagon. In the pentagon, you start with each vertex, you go 2x and you go 3y, you glue a pentagon. There are 5 pentagons you need to glue at each place. So as I mentioned, the also hexagon you should glue. However, in the Dynkin case or Coxeter Dynkin case, it decomposes into square and pentagon. So we don't need to worry about that at the moment. And at each vertex, you can mutate at each cluster. You can mutate as a vertex of the quiver. So there were many 2 cycles, and in fact there were just n 2 cycle because there were n edges, unoriented edges from each cluster. And when you go out and back, these are the 2 cycle. We call this local twist. And the cluster braid group is defined to be the subgroup of the this 2-dimensional CW complex generated by this local twist. And in all the cases we have studied the unoriented class exchange graph is generated by square and pentagon. And if this is true, which people expect to be true in many cases, but not all cases, if this is true, then this cluster braid group we define generated by local twist is in fact the whole fundamental group. And this is just some extra facts. Okay, so we have defined this, and let's see what we get in various cases. So first, I want to talk about Coxeter Dynkin case, although maybe first focus on the Dynkin case. In the Dynkin case, the cluster exchange graph is generated by the unoriented cluster exchange graph. They were just square and pentagon. Like the association of type A3, there were 3 squares and 6 pentagons, which we'll see in a minute again. And in the paper with Wolf, we show that this cluster braid group, which is the whole pi1, is isomorphic to the braid group naturally. Yeah. So although in that paper we didn't define cluster braid group, but it's essentially there. So yeah, we only introduced this notion in a later joint work with Esther, but the credit should go to that paper. So for example, in the 2 case we just talked about, that once you glue square and pentagon to the double the square and double the pentagon, what you get is exactly the braid group of A1 times A1 and the braid group of A2, which is Z2 in this case, because it's easy to see that this CW complex is actually a torus. And here, the CW complex is not a surface. However, the pi1 is BR3. Yeah. And recently, we extended this result to all other cases in the Coxeter Dynkin diagrams. So in the non-simply laced case BCFG, you can use folding, which is easy, but we can also use weighted folding to deal H3, H4, and I2H. And the point is that based on the work of Heng and Dufrio and Tomakin, so I have this preprint with shouting that we can show that the generalized association of any Coxeter Dynkin type, so A, B, C, D, E, F, G, H, I, can be realized as some fusion stable class exchange graph of ADE type. So use this fusion notion, basically weighted case can be obtained from simply laced case. And in the joint work with Heping and Han Zhe, we actually calculate all the cluster braid group in Coxeter Dynkin case, including say B3 and H3. So I think this is a very beautiful set of pictures. So this is type A3. So you have 3. This is the unoriented version. So you have 3 square and 6 pentagon. And in B3, you have 4 square and 4 pentagon, but you have also 4 hexagon. And in H3, you have heptagon. So in the non-simply laced case, the pi1 of unoriented exchange graph is not just square and pentagon, but also n plus 2 gon. So that's the first thing you need to notice. So when you have W plus 2 gong, W is the weight in the Coxeter diagram, then you have W plus 2 gong, and then when you double it, you need to glue x squared equals ym, which generalizes square and pentagon. But that's what you do. And after you do that, you can generalize the ADE case to or Coxeter case that the braid group associated to the diagram can be realized as the pi 1 of the cluster braid group. So, so for example, in type H3, you need to double this picture, all the edges double. And for each m plus 2 gong, you need to glue m plus 2 x squared equals ym relation. Yeah, and then you calculate the pi 1 of that, and somehow you can get the braid group. So I think in type A2 is easy to do by hand, but I think in the higher case it's tricky. Yeah, so that's the result in the Coxeter case, and related to this, for example, in my journal work with Wolf, we do this because our motivation is to prove the K-pi1 conjecture for this space. As I mentioned before, this is contractible, proved by Dynkin. And the way we do that is we realize this space as the space of stability condition of the corresponding type. And recently, using the fusion stable technique, we can also deal with BCFGHI case. And we can also show, give a categorical proof that this is contractible to the classical results. And this is based on the work of Bridgeland, which shows that this space can be identified with the Cabial 2 category associated with the corresponding quiver, and you take the space stability condition there and quotient by Seidel-Thomas spherical twist. And Seidel-Thomas spherical twist conjecturally identify with the braid group, which proved by Brav and Thomas in the ADE case, and in BCFGHI, we have another proof using fusion stable stuff. Yeah, but that's kind of the application of why we want to introduce this cluster braid group is we actually want to, we conjecture that this should correspond to the Seidel-Thomas spherical twist group. So next, let me talk about the surface case, which is more interesting. So let's recall the marked surface from cluster theory, which is due to forming Shapiro and Thurston. So this is just a topological surface with some marked points on its boundary and some interior punctures. Although, I mean, in this talk, we won't talk about punctures. The puncture case are ongoing work with Zhou Yu. And on this marked surface, you have some arcs, which we call the open arcs because we want to distinguish with something else later. And a triangulation is a collection of arcs, which divides this S into triangles, hence the name. And for each triangle, you can associate with a quiver potential by the work of Navadini. And it's very easy that each arc corresponds to a vertex, and each angle in the triangle corresponds to an arrow. And the potential term just sum the three cycles in the unpunctured case. In the puncture, you also have another term, but that's very technical. So the important thing is the combinatorics of classic exchange graph can be identified with the flip of triangulations. So what is a flip? A flip is that you take a triangulation, you replace one of the edge with another diagonal in the two triangle forming a square containing that edge. So for example, you can take the 5 triangulation of a pentagon, and the flip, like here, is just flip this edge, you get that diagonal, you get another triangulation. So that's why I skip the detailed definition of mutation in class algebra or class category, because in the surface case, it's very easy. It's just flipping the diagonal in a square. And then you can get this class exchange graph. So as I mentioned, that's kind of all the information I need to take from the cluster theory. Yeah, so basically in the surface case, if you give me a marked surface, and then we can produce this class exchange graph as exchange graph of triangulation easily. But how the braid group come to play is actually you want to consider the decorated version of this marked surface, which is that in FST's marked surface, one should add a set of decoration. This should meaning my motivation is to study the 3 Cabell category associated with the equivalent potential. And from that point of view, this is the right thing to do. So after you add the decoration, you still have the open arcs as before, which connecting points in the mark points to the marked points in M. But because we have the new decoration, so you also have this another type of arcs, which we call the closed arc. And we will consider the set of closed arc which they have distinct endpoints. And when we consider triangulations with decoration, we want to have a collection of open arcs that divides the surface into triangles, each of which containing one triangle. So the number of decorations is determined actually by the number of triangles of the marked surface, which is a fixed numerical data from S and M. And once you have the decoration, you can, first of all, you still have the equivalent potential associated with that. And the thing that changes is the flip. So basically, originally, if you have just a square, if you flip a diagonal to another one and you flip again, you will come back. However, if you add some decoration in the middle, and the flip should be moving the endpoint of this arc along the edges within the square containing this diagonal, then you cannot come back because there's a direction. And 2 steps of flipping locally correspond to a braid twist, which we define here. So a braid twist is basically, if you think at the beginning we draw this picture, when you have a braid, you twist the neighbor decorations. So if you draw that just on a 2D surface, and you can represent that by this twist. And what does it mean is that if you have a homomorphism from this disk to there, and mapping this dashed line and red line to this dashed line and red line, it determines homomorphism up to isotropy, because if you cut this line, you will get 2 disks. And I mentioned that for each disk, if you know its boundary, where it goes, the rest will determine up to isotropy. Yeah, so this is a braid twist, which is actually the generator for the mapping class group of the surface. Yeah, so the composition of flips correspond to braid twist. And now you still can consider the exchange graph of decorated triangulation. And unlike the unoriented case, for a pentagon, if you have no decoration, you have just 5 triangulation, and they forming this also a pentagon by accident. But if you have decorations in the middle, and you consider the exchange graph, it will be much larger. It's an infinite graph. However, the key thing is that you still have oriented pentagon in this exchange graph. And as you see, this is actually, you go 2 steps from one side and 3 steps from the other side. So this is where we came up with x squared equals y cubed, because they really exist and live in this oriented exchange graph of decorated triangulation. So that's kind of the phase we want to add. Yeah. So the braid twist group I introduced is the subgroup of the mapping class group generated by all this braid twist. And the key thing is that this generalization of braid group is different from the surface braid group I mentioned at the beginning, because I mean, like 10 years ago, I didn't know the difference. So I checked the literature, and the topologists have this declaration, has this generalization of classical braid group, just as pi one of configuration space. However, from cluster point of view, we want a little bit smaller braid group, which I call braid twist group. Yeah, later we'll see why this is the correct definition. Yeah, but in the classical case, they are all equal, so you cannot tell the difference. But once you have more higher genus or more boundary components, this one is strictly smaller than this one. Yeah, so for this braid group, braid twist group, we together with Joey, we have some presentation. And the way we write down the presentation is really writing down it in the style of classical braid group associated with Coxeter Dynkin diagram. So each vertex give you some generator, and the edges gives you commutative or braid relation. However, there's one more relation we need to consider, which contributes from the terms in the potential. So for example, if you have a 3-cycle term in the potential, say 1 to 2 to 3, and the 3 generator B1, B2, B3 should have this relation in the braid group. And so this is also known to topologists to some degree, but they don't know the potential in some sense. So when you have a more complicated cruise potential, you have more terms. So that's all the relation you want to add. And once you add those, the braid group associated to a quiver potential gives you a presentation of the braid twist group I just defined. So the first thing is that actually, when you choose a triangulation, if you take the dual graph, the dual graph will consist of closed arc. So for example, for example, here you have a triangulation. You take the dual graph, you will have this red arc and this red arc connecting the corresponding decoration. And those two are closed arc, and you can take the braid twist along that. So what I'm saying is that once you take a triangulation and you take the dual graph, and for each dual closed arc, you take a braid twist, that will give you a set of generator for the braid twist group. And moreover, Joey and I work out a precise presentation for the braid twist group. Yeah, so this group, you can write it down explicitly. Of course, this is built on the some work from topologists. And what is the point to putting all the things together is, first we want to mention that already topologist knows that the classic exchange graph for the surface, the pi one, is really generated by square and pentagon. And so the pi one of cluster braid, the pi one of the cluster braid group is just the whole pi one of the 2-dimensional C-double complex we introduced before. And moreover, yeah, when you have a decorated version, so the decorated version, the classic exchange graph, the exchange graph of triangulation, naturally is a covering of the this exchange graph of triangulation without decoration. And naturally, the covering group is the surface braid group. However, why we want this braid twist group is we want to take a kinetic component of the exchange graph of decorated triangulation. And if you do that, the covering group shrinks a little bit. And moreover, a key thing is that, so for this unoriented classic exchange graph, we know it's generated by square and pentagon. And surprisingly, that if you take the decorated triangulation, the exchange graph of that is much bigger. It's still generated by square and pentagon, and also technical hexagon. Yeah, so that's one of the key things we have. And because of that, we can prove the cluster braid group, which is the whole pi 1 here, is the braid twist group I introduced before. Yeah, so it's kind of me and also with my collaborator, we introduce a couple of groups, but the motivation is always we want to understand the spherical twist group or the proper generalization of braid group from cluster point of view. So this BT is just a topological realization using the mapping class group. So we're taking a subgroup there. And here, the cluster braid group, basically, we are using the combinatorics of cluster theory and kind of artificially produce a group because we have much control there, and we show these two are the same. Yeah, so combining everything we know is that the cluster braid group is the same as braid twist group, is also have a presentation with respect to the quiver's potential. So each vertex of the quiver gives you a generator, the arrows gives you relation, and also the potential. And we expect that, so now we only improve the Dynkin case or Coxeter Dynkin case or the surface case without puncture. But we expect that this should be true in general up to something, yeah. So for example, first, maybe you want the unoriented classic exchange graph generated by square and pentagon. But that's not always true, I think. So we should expect this up to some modification. So I'm writing a paper with Joey at the moment to extend this result to the case when there are punctures. Yeah, so now I can talk about some application to quadratic differentials. So I only learned quadratic differentials 10 years ago when the paper of Bridge and Smith came out. So a quadratic differential on a Riemann surface is just a section of the tensor square of the cotangent bundle, but we are considering the meromorphic quadratic differential. So locally, it's very easy. It's just given by this form. So you have some function, and you just have dz tensor square. So that's the dz is the cotangent bundle. Then for this function, it's possible to have zeros. And then locally, it looks like z to the k, when k is bigger or equal than 1, you have zeros. You can also have poles. So meromorphic means that you allow poles, especially higher order poles. And these two set of things are critical points. So for example, on CP1, you can have a global quadratic differential. Just you give me a polynomial, and I use this polynomial as the local function, and to have a quadratic differential like that. And for this quadratic differential at the infinity, so if you take z to the if you take w to 1 over z, and you can easily see that at infinity it's a pole of order n plus 5. And if this polynomial has non-zero discriminant, then this function on C will have n plus 1, 0, each of which is a simple 0. Yeah, so yeah, this is just polynomials on C, or really CP1 when you consider the compactification of C. And the important structure is foliation in the theory of quadratic differential, which is that first you have this local coordinate, but you can choose a distinguished local coordinate calculated by this formula. So basically, you want to use this distinguished coordinate to write the quadratic differential just as dw tensor square. Because for these distinguished coordinates, you can put back the metric from C and also define the horizontal foliation, which is just this formula. So if you think on a complex plane, when you have IMZ equals 1, this defines the horizontal line. So that's the horizontal foliation in the just on C for the trivial case. And on a Riemann surface, when you have quadratic differential, you want to pull back using this distinguished coordinate, pull back this kind of parallel horizontal line from C to your Riemann surface. Then that's foliation. And then you can have geodesic. So maybe I shouldn't mention triangulation here, but you can have geodesic. So for example, what you get, so at a normal point, a regular point, if you take a neighborhood, the horizontal foliation you put back from C is just like a parallel of lines. Yeah, so that's a regular point. However, at the zeros, something else will happen. So when you have Z dz tensor square, and if you take the distinguished coordinate, then it's d z to the 3/2 tensor square. And then if you calculate the IM of z 3/2 equals 0, this is the foliation you get around z. So you have 3 distinguished directions. So this is a simple 0. So z dz tensor square. And for double 0, you have that. And for triple 0, you have that. And you see the pattern. And for pole, it's a little bit different. So for 0, you see that basically around this 0, you are gluing many copies of upper half plane. And if you go to this 0, there will be a finite distance. But at the pole, it's something like that. So this is the simple pole. You still use IMW equals 0 to calculate the foliation, and you have one distinguished foliation here. But unlike the 0, when you nearby, there are only 3 things going to 0. The other thing, the horizontal ones will just passing through. But here, it's kind of everything will go to the this pole. Sorry, this is the pole of order 3, and order 4 and order 5. And you can see the higher order pole. For pole of order 1 and 2 will be a little bit different. And for this talk, I omit this technical part. Yeah, but anyway, for any zeros, any order zeros, and any higher order pole, so at least order 3, the local foliation or trajectories are very easy to draw. So at double pole, something bad will happen in some sense. So we want to omit that for this talk. Yeah. Anyway, so then for Riemann surface with a quadratic differential, we can define the decorated mark surface. So that's the point. So how we do that? At each pole, we do a blow up, a real blow up. So basically replace the pole and its neighborhood by a disk. And on this disk, we will have some marked points, which correspond to the distinguished direction of the pole. So basically, if the pole have order m plus 2, then you will have m distinguished directions, and you will have m marked points. But more importantly, you want to remember the zeros. So if you remember the zeros, then they will decorations. So that's why, I mean, in the class theory, is FST have this marked surface, and because they don't care about the quadratic differential, there's no decoration. But if you care about stability condition or quadratic differential, you should remember the zero. And the remark is that because we want to borrow some technique from class theory, and we want to study triangulation, so the zero will assume to be all simple. So basically, all this picture, the only thing we consider in this talk. And for pole, at the moment, we do not want the punctures which translate to, we want to have a pole have high order. Yeah, but we are working on that anyway. Then we can define the moduli space. So moduli space is just each point is a geometrical object, and in this case is a Riemann surface with a quadratic differential. And actually, and you also want to identify them, but we want to also have framing. So the framing is that you start to have a decorated marked surface, and you consider all the quadratic differential such that if you do the real blow up, do the declaration, you will get the same topological type of this decorated marked surface, meaning that there is a homomorphism from this decorated marked surface to the DMS you construct from the quadratic differential. Yeah, that's just part of the data. Yeah, and you can study the moduli space of quadratic differential, use a decorated marked surface to frame. But of course, you can also forget about the decoration and to have unframed version. Or I mean, in the original work of Bridge and Smith, they actually consider the they don't even use the marked surface to frame. They just say if you can identify them, just identify them. So that's further quotient the symmetry of S. But yeah. So the main application of our work is the exchange graph of triangulation or decorated triangulation. They are the skeleton for this type of moduli space. So previously, we say the exchange graph of decorated marked surface is a covering of the exchange graph of normal triangulation, and the covering group is SBR. And you can just simplify that picture to the moduli space of quadratic differentials. And you can further quotient the symmetry of S to get the real moduli space. But this corresponds to the class exchange graph and or exchange graph of normal triangulation on marked surface. And this corresponds to the exchange graph of decorated marked surface. And as before, we want to take a connected component. So this is where it gets interesting, because for people study quadratic differential, they want to study the topological information, so like pi1 or pi0. So if you calculate pi1 of this, this is not even connected. So what we find is that the number of connected components is parameterized by this quotient group. And in order to study pi1, you need to take a connected component. And in fact, each of which is identified, is isomorphic to each other. So you just take one. And now this will have a covering group of this new Beatrice group to this framed quadratic differential just by marked surface. So this group appear naturally from when you calculate pi1 of quadratic differentials. Yeah, so yeah, the main thing what we can do borrowing techniques from cluster theory is that we can show that this space, when you take a connected component, it is simply connected. And the reason is very simple. So before, when we say for classic exchange graph, it's generated by square and pentagon. And when you go to decorated version, we say there are oriented pentagon and also oriented square, and in fact also hexagon. Yeah, but the point is that for the skeleton of this modular space, that's all the things you have: square, pentagon, and hexagon. And those three things combinatorically in exchange graph really shrink to a point in this modular space, and everything else decompose, every other loop decompose to these three type of things. And that's why we can prove that this is simply connected. Yeah, so that's the main application of how we use cluster and braid group to the study of modular space. So maybe I also mention a couple of recent results, but first I also mention that the work of Bridger and Smith is where I start to learn this quadratic differential, because they show for the three Cabial category associated with equivalence potential from FST's marked surface, the corresponding space of stability condition can be identified with quadratic differential. Although they actually prove this theorem quotient by the braid group. And in the same year, or in 2014, I think Hayden, Kazakov, and Kazevich prove a similar result, but they are dealing with topological Fourier category from surface, and they prove the space of stability condition also identified with framed quadratic differential. And so their modular space include the class of Bridger and Smith type, because in Bridger and Smith they want the 0 to be simple, the pole have some condition, and it's the classical pole. However, in the work of HKK, they can have exceptional exponential type of poles. And Akishi Keda generalized Bridger and Smith result of type A to Calabi-Yau N case, so they can have 0 of arbitrary order, but they need to all be the same. And for my joint work with Alistair, we prove the things I just mentioned, but on this aspect, we prove a covering version of Bridger and Smith, and among other things. Yeah, but now for the past year and this year, in my joint work with Barbera, Muller, and So, and also the joint work with Price and Hayden, we are able to generalize this type of results to more classes. So like in this BMQS, we can show that if you take a vertical quotient between three Cabial categories of equivalence potentials, then for the quotient category, you can also realize the space of stability condition by the corresponding modular space of quadratic differential. And the type is also determined in some way. And in the work of CHQ, we use perverse Schober's to unify almost all the results, previous results of this sort. So basically, perverse Schober's is kind of designed to understand the Fourier type of category associated with surface. Then we can understand objects and intersections, objects and morphisms from the surface, and then we can extend the results. Of course, we need to use many techniques of previous works to unify and generalize this. And one interesting thing is that if you give me a quadratic differential modular space, we basically can construct infinite number of categories with same space of stability condition using either this approach of vertical quotient or really construct new categories. Yeah, but I do not have more time to say about that. So maybe I finish with this table. Is there's a dictionary between geometric, dynamical system side, and also categorical and algebraic side, that how the things correspond. And yeah, thank you.
Thank you very much for a beautiful talk. Okay, if you have a question, please just unmute yourself and ask the question or write it in the chat.
I have one, if I may start. Thanks very much for your talk. I was wondering, when you mentioned these this braid twist group, can you also realize it? Maybe you said it indirectly as a fundamental group of some space, so it's some modification of a configuration space.
Yes, yeah, that's the point. For example, in the Dynkin case, it is the regular part of Cartan subalgebra quotient Y group. If you take that,
okay,
that's the braid group. And also for the topological generalization of braid group, it defined to be the pi1 of a configuration space. And in the quadratic differential, it's kind of you have extra structure. However, if you take the quadratic differential to be trivial, in the sense that you just take like a 0 dz tensor square, and that give you a point in the space, and the quadratic differential can reduce to configuration space. So that is why in quadratic differential you also expect pi1 is similar to pi1 of a configuration space.
Okay, thank you.
I think I have a follow-up question on that. So I've been wondering, is there any relation between this braid twist group and if you realize of a surface, and if you realize your surface as a branched covering, you know, then you can define the symmetric mapping class group? Which
yes. So for example, in my writing with Alistair, there's a classical result that the braid group, which I say is the mapping class group of the disk with decoration. If you take the branch double cover of that, you get a genus G surface with one or two boundary components, and then the braid twist lifts to dan twist along simple closed curve. And of course, on that surface, if you take the symmetric part, you can also realize braid group. That's the and in general, this is also true. And in fact, this is kind of the idea that why this should correspond to spherical twist group, because on the branch double cover, you can further take a symplectic fibration by the work of Ivan Smith, which I do not understand the detail. But the point is that you can construct a threefold, which is in symplectic, and each simple closed curve leads to a Lagrangian sphere. And the dan twist of the simple closed curve becomes the higher dan twist in symplectic world, which categorically we understand as Sato-Thomas spherical twist. And then they should match. So that's kind of the idea. Although, I mean, I don't really understand the construction of how you construct this threefold, but categorically, because Ivan showed that for the derived Foucault category of this threefold, you can take a subcategory generated by Lagrangian sphere, which we understand as the derived category of Kuip's potential. And in the symplectic world, it's more faithful in the sense that for type E braid group, you do not have a faithful geometrical realization, in the sense that if you just take a collection of circles, they intersect like type E type. And if you realize that as on the surface, the dan twist along those simple closed curve generates a group, but it's a quotient group not equal to the braid group of type E. That's very interesting result. But in the corresponding spherical twist case, Brav-Thomas shows that it's still faithful. So the group is generated still. Yeah, so there are some difference, but yes, there's a close relation. When you take the branch double cover, you get a dan twist, which maybe people are more familiar with.
Okay, thank you. And then I have also it's a very sort of I don't know, naive question. Why do you call the open arcs open and the close close?
Yeah, so there are people arguing with me, but I just learned quadratic differential, so my terminology maybe not good. But the point is that for the zero, when you go there, it's finite length. So it's kind of when you have an arc, if you think this at an interval, there's a length which is, and the 2 points is kind of really there. So I call it closed. And when you go to a pole, a market point is kind of you go to infinity. So that kind of interval, kind of like R, so it's open. So I mean, I'm not sure if it's good, but that's my reason.
Okay. Okay, well, it's an explanation. Okay. Okay, thank you.